SwayamPrabha. Digital India. Educated India.
I welcome you all to the session of Thermal Engineering Basic and Applied. Today we shall start our discussion on this new topic, that is vapor compression refrigeration cycle. So, if we recall our previous classes, then we can understand that we have talked about vapor power cycles and we have discussed about those cycles essentially in the context of the development or generation of power. But today we shall discuss about this particular cycle, that is vapor compression refrigeration cycle, essentially a vapor power cycle, but the sole purpose is not to produce power, but to produce refrigeration or refrigerating effect. So, as I said, the sole purpose is to produce refrigerating effect. So, purpose of this particular cycle is to produce refrigerating effect. Now, let us look into this particular cycle and we shall try to analyze the processes those constitute this particular cycle. So, as we can see, the sole purpose is to produce refrigerating effect. And we had seen from our daily life experience from household refrigerator that a compartment needs to be at a temperature always which is, say for example, at minus 10 degree Celsius or minus 5 degree Celsius temperature. So, you know, if we schematically try to draw this particular cycle, then essentially this is the space, say for example, and this space should be always maintained at a temperature which is sub-zero at a sub-zero temperature. So, this is say cold space. So, if we need to maintain the temperature of this particular space at a temperature which is, for example, if it is minus 10 degree Celsius, then certainly you know that to run this we need to have a few mechanical components, electrical components. So, as those components will be running, heat will be generated, and so we need to have always transfer of heat from this particular space to somewhere, so as to the temperature of this particular space will be maintained at a sub-zero temperature. Now, this heat will be taken by a device that is called evaporator. So, this is Q in, and if we recall the steam power cycle, we had seen that the working fluid that we considered for that particular cycle is steam water or water, steam water mixture or water. Now, in this particular cycle as well there is a working fluid, but that working fluid is not water, that working fluid is a special type of working fluid and that working fluid is known as refrigerant. So, I am writing the working fluid is a refrigerant. This is a special type of working fluid. We shall be discussing later what kind of property this particular fluid should have, and this particular type of working fluid is given a name, start with R, and there are different types of refrigerants. We shall be discussing this particular type of fluid later. Now, you know that working fluid will be on receiving heat from this cold space, that working fluid will be evaporated, and that is why this device is known as evaporator. So, this particular working fluid will be having a few distinctive properties, and those properties we shall be discussing later in today's class. So, now on receiving heat, that working fluid will be converted into vapor, and essentially this evaporator is designed in such a way that at the exit of the evaporator we will be getting saturated vapor of that working fluid. So, if we give name, say this is 1. So, at 1 if we write at 1 the refrigerant would be saturated refrigerant, saturated state, and then as I said you that we need to complete the processes, and those processes those processes will eventually form a cycle. So, now that saturated liquid is taken into a compressor. So, this device is basically a compressor. So, this is a compressor on. So, this is a device which is work absorbing device. This is not like a turbine. We had seen that turbine is a work producing device, but to run this compressor we need to supply certain energy always in the form of work. So, this is W in. So, we are supplying work to this compressor, and then this saturated refrigerant, saturated vapor to be precise, this is not the saturated liquid. So, this is saturated vapor of this refrigerant, because evaporator refrigerant will be evaporated. So, essentially we will be getting saturated vapor at the exit of the refrigerator, and that is at the inlet of this compressor. Now, that the sole purpose of providing with this compressor is to develop or build up a pressure, and we will be getting if this is state point 2. So, high pressure refrigerant vapor that would be available at the exit of the compressor. So, essentially compressor is a device which can handle two phase mixture certainly, but we had seen in a steam power cycle a pump is there to raise the pressure of the working fluid from a condenser pressure to the boiler pressure. So, now that high pressure saturated high pressure refrigerant vapor will be now taken into another device that is called condenser, and while passing through the condenser it will release heat. So, Q out, because we need to bring back the original state of the evaporator, original state of the refrigerant at the inlet of the evaporator. So, evaporator on receiving heat from this cold space got evaporated, that refrigerant vapor, that is saturated vapor, is now taken into this compressor, wherein we are supplying energy to run the compressor, and the pressure of that refrigerant will increase, and that refrigerant which is available at the exit of the compressor is now taken into this condenser, and by releasing heat while passing through the condenser, the refrigerant will be taken to another device. So, if we give name, this is point 3. Now, question is, in this case we could have install another one device to produce work, and that is what we had seen in a steam power cycle. So, we could have in a steam power cycle we had seen that turbine, basically steam is allowed to expand. So, while steam is expanding, it does work on the rotating part of the wheel, and we are getting work output, rather we get work output. So, here what is done, instead of a turbine, a special type of device that is considered, because here the purpose is not to produce work, but to get refrigeration or refrigerating effect. So, the special device which is considered here is known as throttle valve. So, this is known as throttle valve. And the sole purpose of providing this throttle valve is, the sole purpose of providing with this throttle valve in the circuit is to expand that high pressure refrigerant that comes out from the condenser to the evaporator pressure. So, this is the total circuit. So, let me tell you once again, we are getting high pressure refrigerant at the inlet of the condenser. By releasing certain amount of heat from the condenser, that refrigerant which is available at the exit of the condenser is taken into another device, that is a special type of device, perhaps you have studied in thermodynamics, that is called throttle valve. So, while steam is passing through this throttle valve, it will expand, and this is a very fast process, pressure will decrease, and the purpose of providing with this throttle valve in this circuit is to reduce the pressure of the refrigerant from condenser pressure to the evaporator pressure. So, this is the circuit. Now, as I said you that sole purpose is to get the refrigerating effect, and we have also discussed many times that whenever we consider any mechanical component or mechanical device, and those mechanical components, when those components are there in a circuit or in a cycle, essentially if we need to measure the performance of the cycle itself, we need to map all those processes in several thermodynamic planes. One of the most important thermodynamic planes is the TS diagram, wherein we can represent all these processes. We have discussed that if we can represent any process in TS plane, and area under the process line in TS plane will give us the direct measurement of energy that is either added to the device or energy getting extracted from this device. So, following this discussion which we had earlier, and also with this understanding let us now move to draw the TS diagram corresponding to this cycle, rather corresponding to the processes those are there to constitute this cycle. So, if we try to draw the TS plane, so now try to understand this point is 4 and this is this cycle. So, cyclic process. What we have discussed, that this evaporator will be designed in such a way that at this evaporator pressure, and of course, when the circuit or cycle is designed, certainly evaporator is designed to produce saturated refrigerant vapor. So, now state point 1 is saturated state, that is saturated vapor of the refrigerant. Right. So, that means let us consider point 1 is here. So, this is point 1, this is point 1. Then again evaporator pressure is less than the pressure at which condenser is operating. So, we need to raise the pressure of the working fluid from evaporator pressure to the condenser pressure, and that is why this compressor is there. So, the compressor will now compress this saturated vapor from state point 1 to state point 2, following if we assume that it is a reversible adiabatic compression. So, basically I should say that with this assumption that the process that will occur in this compressor is reversible adiabatic process. So, with this idealized assumption, I should say that this is ideal vapor compression refrigeration cycle. So, this is I am writing ideal vapor compression refrigeration cycle. Why? Because in practical case it is very difficult to have a process which should be reversible adiabatic, but here we are considering this particular assumption, and that is why we are writing this is ideal vapor compression refrigeration cycle, because this is an idealized assumption. Not only here, we also will consider a few more assumptions to analyze this cycle, and that is why I said considering a few idealized assumptions. So, now this is the evaporator pressure, and say this is state point 2, that is the compression process, and if we consider this is the this pressure, that is P condenser, and this is P evaporator. Right. So, what we can understand that now process 1 to 2 is reversible adiabatic process, the compression process. Now, state point 2 is the exit state of compressor or inlet of the condenser. Now, that is there is basically condensation, but we have also discussed that even in the context of steam power cycle, we have discussed about this particular aspect, that designing a condenser which will allow us to have partial condensation is very difficult. So, here also the condenser is provided with this cycle or circuit to allow not the partial condensation, but to have condensation up to this saturated liquid. So, this is state point 3, that is on the saturated liquid line, and this is the process. Now, consider one important case, that what about the process 3 to 4? Process 3 to 4 that we can see from the schematic, that is the throttling process. The throttling process is a very fast process. So, it is basically kind of the expansion of the refrigerant vapor, and the sole purpose is to reduce the pressure of the working fluid from condenser pressure to the evaporator pressure. Now, perhaps you have studied this particular topic in your basic thermodynamics course. The throttling is a very fast process. Since it is very since it is a very fast process, so the intermediate states may not attain equilibrium, and hence it is very difficult to map this process by a solid line, because it is very difficult to understand by which, rather it is very difficult to get the path by which the state point 3 will now change from this to state point 4. Let me tell you once again, throttling is a very fast process, and the intermediate states may not attain equilibrium. Hence, if we need to map the process 3 to 4 in the TS plane here, then it is very difficult to get the path by which the state point 3 has now changed to state point 4, and hence this particular process is shown by this dotted line. So, this is 4. So, this is basically 1, 2, 3, 4, that is the 4 different state points we could map in this TS plane. Let me tell you one thing, because whenever we have discussed any cycle in the context of steam power cycle, also in the context of gas power cycle, we have assumed that all the processes are internally reversible. Those processes may not be externally reversible, but we could map all those processes assuming that the processes are internally reversible, and hence we could use this solid line. But in this particular case, since throttling is a process which is not an internally reversible process as well, so that is why this process is shown by this dotted line. What we can understand from this TS plane, also from this schematic depiction of this ideal vapor compression refrigeration cycle, that the process that is there in this evaporator essentially conversion of state point 4 into state point 1. So, that process occurs at a constant pressure. So, we can see from this TS plane. On the other hand, refrigerant vapors changes its state from state 2 to state 3 in this condenser, and the process occurs at a constant pressure process, at constant pressure. So, this is also a constant pressure process. So, these two processes are constant pressure processes, while the process that is there in this throttle valve, that is not, we can say that the enthalpy is remaining constant all throughout the process, but enthalpy at state point 3 is equal to enthalpy at state point 4. So, enthalpy before throttling is equal to the enthalpy after throttling. So, basically if we write here that enthalpy before throttling is equal to the enthalpy of the working fluid after throttling. So, that means H 3 equal to H 4. Maybe the enthalpy at intermediate states, at intermediate state, or enthalpy at many intermediate states may not be equal, but enthalpy before throttling is equal to enthalpy after throttling. So, what we can understand, out of these 4 processes, 2 processes occur at a constant pressure, while another one process, that is very important process and interesting process as well, which is occurring at constant enthalpy. So, next objective should be to plot all these processes or map all these processes in another plane, that is called pH plane. So, try to understand, for the steam power cycles we had also tried to map all the processes in PV diagram, but here since 2 processes are at constant pressure and one process is at not constant enthalpy, but enthalpy before throttling is equal to enthalpy after throttling. So, we can map the processes now, all these processes in this pH plane. Pressure enthalpy plane. So, if we now map these processes, so again starting point should be 1, because that is the saturated vapor at the exit of the evaporator. So, if we consider this point is 1, right, certainly pressure would be constant pressure. So, let us assume this is the pressure line. We really do not know where point 4 would be, but we can understand from this TS plane that point 4 is basically it is so at the inlet of the evaporator, the state point is not the saturated liquid. So, it is 2 phase mixture. So, now we have identified state point 1 here, then 1 to 2, that is again reversible adiabatic process. So, question is, what would be the enthalpy of state point 2? So, now we also can take point 2 towards right, or where point 2 should be there in pH plane. So, if we apply this TDS relation, that is TDS equal to DH minus VDP. So, process 1 to 2 is reversible adiabatic. So, ds equal to 0, isentropic process. So, if ds equal to 0, then dH equal to Vdp. Compression process, this fellow is always positive, and what about this quantity, because dP is also positive for a compression process, because the sole purpose of having this process is to raise the pressure in the direction of working fluid flow. So, dP is positive. So, essentially dH is positive, that means enthalpy will increase. So, from this discussion, now we can map, we can identify state point 2, say this is state point 2. So, this is state point 2. What about process 2 to 3, that is at a constant pressure process, but point 3, as I said you that partial condensation is not possible. So, we can have the process 2 to 3, that is a constant pressure process, and this point is 3, right. Now, 3 to 4 is basically the throttling process. So, we need to map this 3 to 4 process. So, what I said you that enthalpy at state point 3 is equal to enthalpy at state point 4. So, that means this process should be like this. So, this is 0.4, right. So, this is the pH representation. So, representation of all these processes in pH diagram or pH plane. So, we have discussed, now I forgot to discuss one important point. Question is, comfortably I could locate 0.4 here. Now, where is the guarantee that 0.4 should not be closer to the saturated liquid line? Because then if 0.4 is closer to the saturated liquid line, certainly entropy at state point 4 will be the deciding factor to locate 0.4 in this plane. So, if we can somehow get a clue about the change in entropy of this particular process, from there we can comfortably locate 0.4 in this plane. Now, let us again do this for this particular case. So, again for process 3 to 4, we can write this TDS equal to DH minus VDP, right. Now, state point 3 and state point 4, as I said you that if you start your process at state point 3 and if you go to state point 4, as I said you that enthalpy at state point 4 is equal to enthalpy of state point 4. So, that is equal to 0. What about other this these two? V specific volume is always positive. What about dP? Because if we go back to this, this is an this is a throttle valve acting like an expander. So, basically pressure drops in the direction of the flow of the refrigerant, then dP is negative. So, this is negative. So, essentially try to understand, this is positive, this is negative. So, total is negative, which is again multiplied with negative, so positive. So, that means from this we get ds equal to positive. So, that means for the process 3 to 4, that is throttling process, as you move from state point 3 to state point 4, entropy will increase, though I could locate this point 4 comfortably by this, but this is the correct. So, that means entropy increases as the process 3 to 4 takes place in this expander. So, with this understanding, now let me discuss one important thing, that so even for the steam powered cycle, we had tried to compare the performance of Rankine cycle and its modified versions with the Carnot cycle. So, again it would be wise to again see if we try to compare the performance, or if we compare the process or all these processes with the Carnot cycle. So, let me tell you once again, if it is a Carnot cycle, so if we go to the next slide, so if we try to draw, and we had seen so this is what just I am redrawing the TS diagram here. So, we can see 4 to 1 constant pressure evaporation, 1 to 2 reversible adiabatic compression, 2 to 3 constant pressure process that is occurring inside the or in a condenser, and 3 to 4 that is the throttling process. So, this is the throttling process. Now, had it been a Carnot cycle, then certainly the processes would have been different, and we now discuss the if the cycle had we tried to measure the performance using the Carnot cycle, what would have been the differences. So, now let us consider this aspect. As we had seen, the Carnot cycle, again this reversible adiabatic process will remain reversible adiabatic, but instead of a dry compression that we can see, because this ideal vapor compression refrigeration cycle, this 1 to 2 is basically reversible adiabatic compression. So, this is dry compression. Why it is dry? Because try to understand the refrigerant or working fluid available at the inlet of this compressor is saturated. It is not a two phase mixture. So, basically it is called dry compression. Dry compression or dry compressions are preferred to the wet compression because of several advantages that I will be discussing today. So, basically as I said you, we are now trying to compare all these processes with those had we considered this cycle to be a Carnot cycle. Then this compression process will be the reversible adiabatic process, but the actual process between these two temperature limits will be like this. So, this is 1 prime, say this is 2 prime. Similarly, instead of a throttle valve, we need to use a reversible adiabatic expander to have this reduction in pressure from condenser pressure to this evaporator pressure. So, that means this process 3 to 4 will be again this. So, this is 4 prime. So, now if I write 1 prime, 2 prime, 3, 4 prime, so this is the Carnot cycle, right. Whereas, ideal vapor compression refrigeration cycle, that is 1, 2, 3, 4. So, what are the differences? First of all, the compression process is now wet compression. So, this compression 1 prime to 2 prime, that is again reversible adiabatic compression, but that is wet compression. Why it is wet? Because you can understand point or state point 1, state of the working fluid corresponding to this point 1 prime is not a saturated vapor. So, this is a two phase mixture. So, that time compressor needs to handle this two phase mixture. Now, handling two phase mixture is indeed a challenging task. Why it is so, I will be discussing soon. And 3 to 4 prime, now that is the process that will occur in a reversible adiabatic expander. So, this process is also reversible adiabatic process. So, 3 to 4 prime will occur in a reversible adiabatic expander, because the sole purpose is to reduce the pressure. So, why Carnot cycle is not preferred? Because the most important part is this compression process, that is wet compression. What will happen? Because we know compressibility of liquid and vapor is not same. So, liquid and vapor, since the compressibility of these two is different, then liquid and vapor being compressed differently will create an very detrimental phenomenon that is known as lubricant washout phenomenon. What is this? First of all, since now had we considered Carnot cycle, in this case compressor needs to handle two phase mixture, and liquid and vapor, these two are having different compressibility. So, liquid will now rise with the piston, that is the working fluid will now, when it would be compressed, the liquid refrigerant that would be there in the cylinder head, and when the piston is rising, and that liquid refrigerant will create or will damage the valves and etc. Not only that, as I said you that liquid vapor being compressed differently, the liquid phenomenon will be there, wherein liquid molecule will try to penetrate into the gap between piston and cylinder wall. So, typically the gap between piston and cylinder wall is filled with a lubricant. Now, when that liquid molecule will be there, or when liquid molecule will penetrate into this passage, that will wash away the lubricants, and this phenomenon is known as lubricant wash away phenomena. So, considering these two, wet compression is not preferred and rather dry compression, that is 1 to 2 is preferred, and that is why a variant of this cycle, ideal vapor compression refrigeration cycle, is preferred over the Carnot cycle. So, now with this let us try to discuss that essentially what we are looking for by studying this particular cycle. We need to obtain the refrigerating effect or refrigeration effect. What is that? Refrigerating effect or refrigeration effect is essentially, if we look at the schematic, what would be the extraction of energy from this cold space per unit mass flow rate of the refrigerant. So, that would be the refrigerating effect. Typically that particular effect is represented or expressed in terms of tons of refrigeration. I will be discussing this. So, let me tell you once again, we are studying this particular cycle essentially to understand the refrigerating effect. What does it mean? It means the amount of energy that would be extracted from the cold space per unit mass flow rate of this working substance, that is refrigerant. So, now if we consider this particular part, because any cycle, as I said you, finally we need to measure the performance, and the sole purpose of this cycle is to get the refrigerating effect at the cost of some input energy, that is the work input or work added to the compressor. So, we are supplying this much amount of energy to run this cycle, and at the cost of that input energy we are getting some desired output or desired effect, that is the refrigerating effect. So, now let us consider steady state steady flow equation. If we assume that the steady state has reached, and if we consider that 1 kg of the working fluid, that is refrigerant. So, then if we just apply the steady state steady flow equation across all the components, if we go back to this slide, if we assume that processes, all the processes are now at a steady state, I mean all processes got steady state situation scenario, and then if we consider the working fluid is 1 kg. So, per kg of working fluid, if we apply that steady state steady flow equation across this evaporator, what we can write? We can write that, so evaporator, we can write H4 Q in equal to H1. So, therefore, Q in equal to H1 minus H4. So, that is what is very important, H1 minus H4, right. So, this is of course unit is kilojoule per kg. So, this is kilojoule per kg. Now, this much amount of energy, this much amount of heat this evaporator is taking per kg of refrigerant flow at the cost of some input energy, and that input energy is the work input or work addition to the compressor. So, if we apply steady state steady flow equation across the compressor, then we can write, if we go back to this schematic depiction, then if we apply the steady flow energy equation, steady flow equation across this compressor, we can write, I mean just we are writing this, and we can write H1 plus W in equal to H 2, that is W in equal to H 2 minus H 1. So, now try to understand. So, this is basically input energy in the form of work. So, this is input energy and this is the desired effect. Right. So, we can define now coefficient of performance. For any refrigeration cycle we cannot define efficiency, that we have discussed. Now, you also have studied when you have studied second law of thermodynamics. So, coefficient of performance COP, that is desired effect to the input power or input energy, I should say. So, that means this is H 1 minus H 4 divided by H 2 minus H 1. This is also the unit is kilojoule per kg. So, try to understand, this is the mathematical expression of the coefficient of performance and essentially per unit mass flow rate of working fluid, the change in enthalpy is giving us an estimate about the desired effect and input energy. So, if COP is higher, then the performance of the refrigeration cycle will be better. So, higher is the COP, better the performance of the refrigeration cycle is. So, that is what we can understand. So, we have to calculate COP to get an estimate about the performance of the cycle. Higher will be the value of COP, better the performance of the cycle will be. So, now what is refrigerating effect, that is also very important. So, though I have already discussed about this particular term refrigerating effect or refrigeration effect. What is this? And this is typically denoted by this symbol R. Now, what is refrigeration effect? So, this is essentially had we applied steady state flow equation across this evaporator. So, this is H 1 minus H 4 kilojoule per kg. So, this is H 1 minus H 4. So, as I said few minutes back that the amount of energy that would be extracted by the evaporator, by this evaporator, let me go back to the schematic. So, the amount of energy that would be extracted by this evaporator for getting the state of the working fluid changed from state point 4 to state point 1, that is the refrigerating effect, and that refrigerating effect mathematically is H 1 minus H 4. So, this is the refrigerating effect. Now, let me tell you one thing, we shall be solving one numerical problem from this topic as well, but if we try to go back to this TS diagram, we can see that state point 4, that is at the exit of the throttle valve or at the inlet to the evaporator, it is the two phase mixture. So, we need to know what would be the liquid vapor liquid or quality of the refrigerant at the inlet of this evaporator. So, if we try to if we look at this TS plane carefully, then we can write, if we go to this next slide, then we can write that H4, that is the enthalpy at state point 4 should be equal to, so this is at constant pressure and this is P evaporator, right. So, we can write this equal to H so basically what we can write, so this is H1 plus X4, so this is HF at P condenser equal to X4 HFG at P condenser. So, this is P evaporator, sorry, this is P evaporator. So, this is P evaporator, right. So, essentially this is H4, that is HF. So, this is HF plus HFG. Now, what we can write X4, therefore, we can write X4 equal to H4 minus HF at P evaporator divided by HFG at P evaporator. Now, what about if we go to the next slide, then we can write that X4, that is H4 minus HF at P evaporator divided by HFG at P evaporator. What about H4? Because we have discussed that H4 equal to H3, that is enthalpy of the working fluid after throttling is equal to enthalpy of the working fluid before throttling. And what about H3? That is HF at the condenser pressure, that we can see from the stage diagram. So, this is H3 or minus HF at P evaporator divided by HFG at P evaporator. So, this is HF at P condenser minus HF at P evaporator divided by HF at P evaporator. So, this X4, this quantity is very important and it is known as flash gas fraction. So, this is known as flash gas fraction. What does it mean? So, basically mass fraction of liquid in this liquid vapor mixture. So, basically this is, if I write, so this is mass fraction of liquid in liquid vapor mixture. So, this is important to know to the designer who will be designing this evaporator, because you can see that the inlet condition of the working fluid is two phase mixture before it enters to this evaporator. So, now the designers should know the quality, and that is what we could establish here, and that is known as mass fraction of liquid in the liquid vapor mixture and known as fly gas fraction. So, to summarize today's discussion, we have discussed about the ideal vapor compression refrigeration cycle. We have tried to understand all the processes constitute this cycle. We have mapped all those processes in two different thermodynamic planes. From there, we have tried to quantify what is the coefficient of performance and the refrigerating effect. In this context, we have also discussed about several critical issues which are very important to know for about this particular cycle. With this, I stop here today, and we shall continue our discussion in the next class. Thank you.